In this lesson, we're going to talk about arc length or curve length. I use both terminologies because sometimes people think of an arc as only a piece of a circle. This will apply to any curve like the one I've given here. So we'll start with a general curve, and if you want to find the length of this, you can see I've added some little points to it. So I have a purple graph here and then a couple of greenish points. One way to approximate the length of that curve would be to connect these dots using line segments. So I've crudely done this, and let's call this first point P0 or P naught. The next one is P1, and then there's a lot of them, so I'm saying dot dot dot, and let's make the last one P sub n. And in doing this, what it allows us to do is, since we use P sub n, we're going to take n of these segments, and eventually what we'll do is we'll let n go to infinity, and when n goes to infinity, it'll make each of the segments really small, and they'll get really, really close to approximating what the length of each curve is. So our goal is going to be to develop the arc length. I'm going to call that big L, and we'll start by defining big L as the limit as n approaches infinity of the distance from P sub I minus 1 to the point P sub I. I've left off my sigma. This might look a little confusing here. Just think of it as like this AB would be the length of the segment going from point A to point B. So we're just using sort of like the magnitude bars here for that. So that's just a notational issue. And now we have to think about, before we do any infinite sums, we need to name this P sub I minus 1 to P sub I. In other words, we need to put this in terms of x and y. Hopefully at the end have it in terms of x, and then if we have a different function that's written a different way, we can have it in terms of y. So hopefully everybody agrees that if you take the x value and you subtract it from the x value of this point, and you subtract it from the x value of this point and square it, and then add that to the y values subtracted and squared, that's the distance. So that's a fine statement of the distance. It's just using distance formula or Pythagorean theorem. Problem we'll have is how do we put this in a nice form where in the end we get a function that we can integrate. Remember, if we're looking to add up infinitely many things, that's what integrals are really good at. So eventually we'll take this, we'll simplify this, and then we'll put it into an integral. So you can think of this as delta x squared and delta y squared. So the notation admittedly here is not going to be amazing. Let's allow delta x to just be fixed. So every time we go over by a certain number delta x units where we keep that distance constant, we don't flex the distance. And the change in y, each change in y could be different depending on what particular segment you're on. For example, this green segment went up pretty steeply. This one was relatively flat. So we need to allow for the change in y to change with different points. So we need to figure out some way to express this guy, the delta y sub I, using some x's. And one way we're going to do that is we're going to use the mean value theorem. So the mean value theorem, we'll have a little aside here. Let me just scoot the camera over. Mean value theorem. One easy statement of this is, for example, f prime of somewhere, that's x sub I star. that somewhere, if you go on a continuous and differentiable function, those are two big restrictions. We need it to be continuous and differentiable. Or if it's just differentiable, obviously it's continuous. That you can find a spot whose instantaneous rate of change is equal to the average rate of change. And the average rate of change is also known as the slope. So these are f of x sub I minus f of x sub I minus 1, and then the inputs x sub I and x sub I minus 1 are subtracted. So this is just glorified slope. So you can think of this bottom guy as delta x. And then the top one is delta y sub I, because delta x we're fixing again because we're saying that our segments are going to be restricted to one particular length. Delta y is going to be different every time, as we already discussed, or possibly can be different every time. And that's equal to some f prime inside the interval. This x sub I star has to live somewhere between x sub I and x sub I minus 1. And then we can manipulate that equation to find that delta y sub I has to equal f prime of x sub I star times delta x. And that is what we're going to sub in. So we got our delta y here, and we have a restated delta, restated in terms of x. So we're going to replace delta y sub I. This distance between the 2 points now becomes the root of delta x squared plus the replaced value for delta y sub I. It's all of that squared. And now you see that there's a delta x squared and a delta x squared. And given that it's in a square root, we can actually peel a delta x out of, factor it out of the root. So this is squared and it came out, so now we're left with 1 in the place of delta x squared. And this delta x squared also got factored out. So we were effectively left with just f prime of x sub I squared added to 1. So now we're going to take this expression and put it back in for L. So these are all equal to p sub I minus 1 to p sub I. That's a p sub I minus 1 to p sub I, and that one is as well. So back up here, this is what we were trying to find an argument for. So this expression that we have will be subbed in here. I'm going to do it over here. So L will equal the limit as n goes to infinity of the sum as I goes from 1 to n of our new expression for p sub I to p sub I minus 1. I'm going to do one little thing, which is just, you'll see why in a second, but I'm going to flip the order. In other words, I'm keeping delta x out of the root, but I've moved delta x to the right side. And that's just so that you begin to, it begins to more directly evoke thoughts of integrals. So this is our new L formula. And again, I will say some of this notation is not the best. It's not completely rigorous. But we're going to now have our arc length. We have an infinite sum of this delta x. And in the world of integration, the infinite sum delta x becomes integral dx. And instead of p0, p0, and pn, we're looking only in terms of x. So we're going to do from a to b. I know that I'm just introducing this lettering a and b, but you can think of a is just the beginning x value, b is just the ending x value. And this is just 1, of course. Now, f prime of x sub I star, that's tracking the derivative of every point. And if we're looking at the derivative everywhere, then we can just call the thing dy dx. So this is our arc length formula. And I do agree that there's a couple little notational things that I've just hand waved or skipped over. But the end result is we took a limit of a bunch of segments lengths. We rewrote the segment length using mean value theorem. We rewrote the segments lengths all in terms of x. And then we realized that that infinite sum can be done by an integral. Okay, we can also write this. I'm going to erase a lot of this derivation now. We can also write this. That's for a function that's y in terms of x. But it really doesn't matter which variable is which. We could write the same exact thing using an x in terms of y. So think about like y equals x squared, right? Y equals x squared is, of course, this graph. So in this graph, it's a lot easier to, I guess, to think about dy dx is 2x. But maybe if you're given an equation like x, well, let's just rewrite this one. X equals root y. So now you have x in terms of y, same function, but dy dx is a bit annoying to deal with here. So we could rewrite this thing. This is rewriting it in terms of y. So we're still going to integrate, and 1 is still 1. But instead of dy dx, we go dx dy. And then we integrate dy. And if that seems like, well, you just jumped right to it and you didn't provide any explanation, fair. But it's pretty easy to see how this will work. So think of this dx, dy dx as squared. One thing that you could do, and I'll get rid of this as soon as I put it in, but you can think of multiplying through by like a dy over dy. And if you put the bottom dy, if you distribute it into the root, then the dy's here will cancel. You can also bring the purple dx in, and you'll see everywhere there was a dy dx, there becomes a dx dy, and then 1 shows up as well. So think about it kind of as multiplying by the reciprocal dx over dy into that integral. I said into the integral, I mean into that square root. And if you do that, you'll get this expression. Okay. Now we'll do an example. So here's the problem. We're going to do find the length of the curve y squared equals x cubed from 1, 1 to 4, 8. And just confirm for yourself real quick that the points 1, 1 and 4, 8 exist on this curve. 1 squared and 1 cubed are obviously the same. 4 cubed and 8 squared, those are the same as well. So those 2 points do live on the curve. And really it's a matter of like picking your values here, or your technique. If we choose to do it dx, I'm going to get rid of the green. If we choose to do it dx, then we need to know what dy dx is. If we choose to do it dy, then we need to know what dx dy is. One important note about this dy notation is now we have some c and d value. I've just named them c and d, but these were x values from a to b. This thing c and d, those are now y values. In other words, if you're integrating dy, you need to plug in the y values of the points. So if we choose to go this method, we're going to be using 1 and 8. Whereas if we go dx, we're going to use 1 and 4. And I'll show you dx first. So if we take this curve, we can rewrite it as y equals x to the 3/2. And now dy dx is pretty simple to find. Dy dx is 3/2 x to the half. Now we can start our integral. The arc length equals, we know we're going from 1 to 4 because we're working dx, x values of 1 and 4. And we take the square root of 1 plus dy dx squared. That's 3/2 x to the half squared. And when you square those, it cleans up a little bit. We're going from 1 to 4. 1 plus 9/4 x to the 1. And then this is an integral. I'm not going to do it here because the primary importance of this video lesson is arc length or curve length, and I don't want to go off on too long of a tangent and make the video too long. But this is an integral that you could do. It's not too hard. Do a u substitution. If you let u equal 1 plus 9/4 x, you can rewrite this integral in a pretty friendly way and integrate it from there. I do have the answer. It is a 27th times 80 root 10 minus 13 root 13. So you can integrate it, whatever form you have, you can ask your calculator for a decimal approximation, and this is going to be the exact correct answer. I'm just going to double check that I wrote everything correctly there, yes. So that's one way to do it. That's if we did the whole thing dx. Now I'm going to get rid of that work and work it all dy. So if we're doing it dy, we need to know what x is as a function of y. And as a function of y, x is y to the 2/3. So then dx dy, we're taking the derivative of both sides now with y as the independent variable, will be 2/3 y to the negative 1/3. So that is the thing that's going to get subbed in for dx dy squared. So our length is equal to, notice that we switched variables, so we can't use 1, 4 anymore. We have to use 1, 8, or the y values. Always start with the square root of 1. And dx dy, which is 2/3 y to the negative 1/3 squared dy, all of that lives under the root. And then you could do the squaring. You get 4/9 y to the negative 2/3 dy. If you integrate that, you'll think about how to do that. If you integrate, you'll get the same result as we got doing it dx, which I've erased. But you get the same result, it's just on dy. You may wonder which one to pick, and I would say, well, go based on, is it easier to write the derivative? And then is it easy to calculate the square of dy dx or dx dy? And which one's going to lead you to an integral that you can more easily do? So in any case, these two things work. It'll work either way. Okay, at this point, I would say if you felt comfortable with everything I've said, you can go through and do some practice. You might want to see, some of you viewing it might say, okay, good enough. Others might want to see how this thing becomes this. So I'm going to do that now. So some may want to just break off and do something else. So I'll start with this thing. All right, so like I said, we'll bring in a dy here. So it's kind of like we're multiplying by 1. Looks like it's pretty hard to see. Try to write it a little more boldly. And now we'll treat dx dy is what's going to come in. So think about this as the square root of dx dy squared. And then I'm just going to keep this dy outside. So now that I've written this, or dx over dy as a root we can distribute it in because they have the same power. So now dx dy, that'll replace 1. But dx squared and dy squared, these are exactly the reciprocal of the two that are given here. And since they're the reciprocal, we yield 1 dy, which is what we've got here. So hopefully that's a pretty good summary of what you need to know for arc length. Again, the quick version is we started by adding a bunch of segments, and then we made the segments very small until we got the exact curve length. Thank you.